The fifth section of this chapter is all about disaccharides. Notice the prefix di. That means two. Remember the word saccharides means sugar. So we're talking about sugars that contain two saccharides, two individual sugars. These are the three that we will be talking about: maltose, lactose, and sucrose. Notice that they have different combinations. For instance, glucose and glucose make up maltose, glucose and galactose make up lactose, and glucose and fructose make up sucrose. It would probably be worth your while to memorize these. Maltose got its name because it's malt sugar. It's the sugar that's derived and used in cereals, candies, and for brewing. These contain two D-glucose molecules, which means D-glucose means that the fifth carbon has the OH on the right-hand side. It forms both alpha and beta. So what they're referring to is the very first carbon, whether it's alpha or beta. Remember, alpha means that the OH group is pointing down on the first carbon, and beta means the OH group is pointing up on the first carbon. That makes a difference in how this bond looks. Because this is alpha is pointing down, it's going to be reacting, and it's always going to be reacting with the first and fourth carbons, which is why it says 1,4 glycosidic bond, because it's the first and fourth carbon of this bond, of this compound, of the individual saccharides. So here's the first and here's the fourth. Since they're both pointing down, they form kind of a V shape to attach to that oxygen. And it becomes oxidized by removing the hydrogens. So if we're looking here, this is lactose, this is not maltose, but I just wanted to give you an example of when it's beta. Notice it's pointing up here. So when it forms, it has one up and one coming down, so they kind of stack on top of each other. So mentally lift the right one up, and you'll find that it forms more of a line, versus this one, which is an alpha, it forms a V. That's the big visual difference, and it's also a big difference in how it reacts. So this forms both maltose forms both alpha and beta. So here is the alpha isomer. Beta would be more of the line. These are two glucoses. Now we have galactose and glucose, and that forms lactose. Remember, the fourth carbon is how you tell galactose and glucose apart. With galactose, the OH is on the top. With glucose, the OH is on the bottom. So it forms with both alpha and beta glucose, which means that this glucose could be pointing up or it could be pointing down. Contains a beta bond, meaning that the first carbon had beta, so therefore it was coming up, which means it forms more of a line versus the other one, which has more of a V. Sucrose is alpha glucose and beta fructose. Notice it's an alpha-beta 1,2 glycosidic bond. That's a mouthful. To look at this visually, it's the first carbon and the second carbon. That's why it says 1,2. The reason why it's the second carbon here is because, remember, this was originally a ketone. And when it collapsed to form this hexagon, or to form this pentagon, this is the first carbon here, so that means this is the second one. The other two did it on opposite sides. This one is more of a stacking. So these two things react to form this ether here, carbon, oxygen, carbon, which is why it's considered an ether, form this bond, alpha, beta. Alpha means that the first that OH group is pointing down. Beta, because the first OH is pointing up. So when they come together, they form a line. But that's where that alpha beta came from the alpha beta here. 1, 2, the first carbon, the second carbon. So alpha, they follow the leader. So alpha goes with 1, beta goes with 2. Glycosidic bond. So if we're looking at this, for this disaccharide, and this is a review of things that we've done for the last few sections, so you might have to refer back. List the two monosaccharides units that are in this bond. So, first thing you want to do is look that it's a hexagon. They are both hexagons, so neither one of them are fructose. If it was a pentagon, then it would have been fructose, but they're not. So the one thing that tells the two apart is the fourth carbon. 1, 2, 3, 4. 1, 2, 3, 4. Remember, if it points up, it's galactose. If it points down, it's glucose. Here's galactose where the fourth carbon is pointing up. So when we go back here, the fourth carbon is pointing up, so this one's galactose. This one then is glucose. Okay, the next thing you want to look at is whether or not it's alpha or beta. So when it's down, it's alpha. When it's up, it's beta. This one, the first carbon is pointing down, so that's alpha. This one is also pointing down, so that's also alpha. Then finally we have to look at D and L. And for the D and L, we have to look at the last chiral. Here's our last chiral. They actually don't have you determining if it's A or... You can't really see if it's D or L. So we're actually going to leave that out. We're just going to say alpha galactose and alpha glucose. The reason why you can't see it is because because when it's a straight line, this O is actually an OH. And so therefore, you can't tell if that was supposed to be originally up or originally down. So I'm just going to leave the D and L out of it, and it's going to be alpha galactose and alpha glucose. Type of glycosidic bond. Well, this is an alpha, and it is on the 5th carbon, actually the 6th carbon. So when we're looking at it, 1st and 6th glycosidic bond, because this is 1, 2, 3, 4, 5, 6. It was getting messy on the other page. That's where the connection is, so that's why it's 6. The first carbon is on the other side. Because this was originally alpha, that's why it is. They didn't even say if it was alpha or beta, but it is alpha on both scenarios because of the OH coming down. Now the sweetness of sugars. Part of the reason that it's so hard to cook with artificial sweeteners is because they're so much sweeter than actual sugar. Here's sugar. That's table sugar. That's the reference point. So if it's less than 100, it's less sugary than sugar. It's less sweet than sugar. If it's more than 100, it's more sweet. It's sweeter than sugar. So if we're looking at this, sorbitol, for instance, is found in a lot of sugar-free gums. It's actually less sweet than sugar. But if we look at like aspartame or saccharin, it's a huge difference between that and sugar, which is why when you use packets, when you are sugaring your iced tea at restaurants, you only use a little bit in comparison to using sugar. A lot of people put 3 or 4 packets of sugar in iced tea, but only a half a packet of saccharin. And that's because of how much sweeter it is. So when we're looking at this, sucralose is very similar to sucrose. The only difference is, here's our glucose on top, and here's originally was the fructose. But you notice here the chlorines, and those chlorines make a huge difference in the amount of sweetness you taste. Here's the aspartame, which is also NutraSweet. This looks absolutely nothing like any sugar that we've seen. But once again, it doesn't digest the same way, and it actually makes it taste sweeter than actual sugar. And that is all for the disaccharides.